So welcome to Math 355 Abstract Algebra. Oh, I loaded up the wrong one. Oh, okay, no, I just used the wrong one in the previous section. All right, so we'll just do section one here. All right, so welcome to 355 Abstract Algebra. This is section 2, so I will just change the one over here to a 2, and now everything will be good. There we go. And so what we're going to do today is we're going to talk about fields and roots. So there's a lot of material to do today, and so we're probably going to end a little bit early just because it is much easier to be the professor at the podium speaking than it is to be the student in the audience listening. And one of the dangers of meeting twice a week is you have longer lessons and there's just sometimes too much information that comes through in a short amount of time. And I want to make sure we have enough time to process everything. So L over F is going to be an extension of field. So for big F, think maybe the rationals or the reals. Let alpha be some element of L. We say that alpha is algebraic over F if it is a root of a non-zero polynomial in F of X. So what is F bracket X? This is going to be all polynomials P of X of the form A0 plus A1X plus ... plus AN X to the N. Each AK is an F. And so I'm not specifying what the degree of the polynomial is. It's just a polynomial of finite degree with coefficients in big F. So you're algebraic if you're a root of a non-zero polynomial like this, otherwise you're transcendental. And we spent a lot of time proving that the rationals are countable. We proved the algebraic numbers are countable. We proved that the interval 0, 1 is uncountable, or the reals are uncountable, which means that almost every real number is non-algebraic. Almost every real number is transcendental. Numbers like e and pi we expect to be transcendental. It's a bit of work to prove them. This is why we spent the time when we did Liouville's theorem, because it led to an easy proof that a certain number, the Liouville number, is transcendental. It's too well approximable by by rationals. And so the question is, why do we care about the results we're proving today? Well, they help us understand the structure of various numbers. Are they algebraic? If they're algebraic, to what degree? And how do these properties of the numbers impact other phenomena? So the fact that the Liouville number is almost rational is what led us to be able to show that it was transcendental. So if I give you the number, the square root of 2 plus 1 plus the cube root of 5, it turns out that that is the root of this monster polynomial over here. As a nice exercise, and you may use Mathematica, ChatGPT, whatever, verify directly that this is a root. Now, this could be your lucky day. I'm being a nice professor. I'm giving you the polynomial. All I'm asking you to do is evaluate the polynomial at this point. So you have to start off by taking the square root of 2 plus 1 plus the cube root of 5, raise that to the 12th power, subtract off 6 times that to the 10th, go through, simplify. So here's my challenge. Can you do this using something like Mathematica? Can you actually show, I'm telling you what the polynomial is, can you show it solves it? And if not, boy, are we in trouble, right? If I can't even show that it solves the polynomial when I'm telling you this is the root. Well, maybe another way is to actually construct the polynomial that it solves. And so what I can do is I can start off with the rationals. And what I can do is I can slowly extend the rationals to larger and larger fields where eventually I know this number is going to live. So does anybody want to give me the first extension of the rationals, the first thing I should add to the rationals in my quest to get to this number? There's 2 natural candidates. What should I add to make the rationals a little bit larger? Which irrational number? You can only add one number at a time. What would you like to add? There's 2 natural candidates. That's one of the 2 candidates. What's the other one? The root of 2. Yeah. Square root of 2 or the cube root of 5? Which would you like to add first? Crude. Okay. Does not matter. So we will add the square root of 2. And so this is now going to be all the things of the form a plus b square root of 2. A and b are rational. Do I have to add the square root of 2 plus 1? Or do I already have that once I've added the square root of 2? I'm sorry? One is already in the rationals. So do I have square root of 2 plus 1? Is that of this form? Can you give me an a and a b so that root 2 plus 1 is of the form a plus b root 2? Yeah, 1 plus 1 root 2. I don't have to do anything special. Once I have added the square root of 2, I get the square root of 2 plus 1 for free. Just as a quick aside, we're defining f of bracket alpha to be the subring coming from a polynomial of finite degree. Let's take alpha to be I, which is the square root of -1. So alpha squared is 1. So if I look at the polynomial, let's say if I look at p of alpha, that would be a0 plus a1i plus a2. What's I squared? What's I cubed? Minus I plus what's I to the 4th? 1. And we can just see then it would be a fifth, I, and so on and so on and so on. So if I give you something like this, if I give you all, if I give you the ring where I adjoin alpha, initially I could have a polynomial of degree n for any n. But what we're seeing is we actually don't need that. I can put all of the evens together, degrees a0 minus a2 plus a4 minus a6 plus ... And I can put all the odd indices together, and I would have a1 minus a3 plus a5 minus a7 plus ... Let's call all of this stuff, let's call it maybe b0, and let's call all of this stuff b1. So even though I could initially have arbitrarily high powers of alpha, we see that because alpha solves the polynomial, so alpha is a root of x squared plus 1 equals 0. Because it satisfies a polynomial of degree 2, I don't need to have anything beyond an alpha term. I can reduce the alpha squared because alpha squared, this implies alpha squared equals -1. So wherever I see an alpha squared, I can replace it with -1. I only need to have two things. I don't have unique ways of writing numbers. If I want to write 2 plus 3i, I could also write that as 2 plus 3i to the 5th. So I don't have a unique way of writing things. That's fine. So when I'm looking at what's going on over here, I don't have to worry about adding that +1 to the square root of 2. That's not needed. What should I add after this? There's two natural things I could do next. So what would be next? So what should I add to q with the square root of 2? I'm sorry? So one is I could add the cube root of 5. And what's the other thing I could add? So one possibility is I could add the cube root of 5. What else am I going to need? There's something else I need in addition to the cube root of 5. It's fine to do the cube root of 5, but I just want to be clear, what else are we going to need? I've got root 2. I can do root 2 plus 1. What else am I going to need to add? Right, the square root of 2 plus 1. So do you want to finish the 2's and then do the cube root of 5, or do you want to do the root 5 and then go back? Which way do you want to go? I would rather finish the 2's myself. And so we'll now add the square root of the square root of 2 plus 1. So notice what I'm doing is my field is q adjoined the square root of 2. And then in parentheses, I'm putting in this new number. It turns out that this is the same as, well, just take the square root of 2 and the square root of the square root of 2 plus 1 together. Because when I'm doing something like this, I'm looking at the smallest field that, here, the first one is the smallest field that contains the rationals and the square root of 2. And that's my field q square root of 2. And then I take the smallest field that contains the q squared of 2 as well as the square root of 2 plus 1. That's the same as just taking the smallest field that contains q and the square root of 2 comma the square root of 2 plus 1. Because I can generate q squareds of 2 by just looking at the beginning. All right, and then what's the last thing I would do? Then the last thing is I would then add, I have square root of 2, square root of the square root of 2 plus 1, and then the cube root of 5. So you could absolutely do that, because if I square the square root of 2 plus 1, that's going to give me the square root of 2 plus 1. And if I subtract 1, that's going to give me the square root of 2. I do not need that. I am not saying that this is the most efficient way to get there. So I could absolutely just jump to, I don't need the square root of 2. And so what you're basically saying is this over here, your claim that this is really just the same as q square root of the square root of 2 plus 1, as the square root of the square root of 2, and why it's having trouble writing is like this time delay. If I square that and I subtract 1, that's the square root of 2. So I don't actually need the square root of 2. Absolutely. And so later on, we'll talk a little bit about what's the fastest way to do something. I am trying to do a methodical procedure, but that is a much faster way to get there. Yes?
Could you just adjoin the entire thing then? Just adjoin it in one
You could. But what I'm trying to do is I'm trying to figure out, how could I build the field that has this? These are much simple things. I know what polynomial satisfies the cube root of 5. I know what polynomial satisfies the square root of 2. And so the hope is, maybe if I understand how to adjoin just one element at a time, I can figure out what those polynomials are, and then maybe I could figure out what that polynomial is. So that's the challenge I'm leaving to you. A professor should be like a magician and not show all their tricks, right? Can you figure out how to find the polynomial that this satisfies? It might even be a challenge to just show that it satisfies that. Can I come up with a procedure that would lead me to it? And this is one possibility. Is I'm trying to break it up into lots of smaller, simpler problems. Each one of these problems, I'm just adjoining a really nice number whose irreducible polynomial I think I understand, whose minimal polynomial I think I understand, and maybe I can somehow combine these and start putting in more and more coefficients. So I will leave this as a challenge for you to think about as to how might you do something like that. Okay, so we talked a little bit about what does this ring look like? And we noticed that if alpha squared equals 1, every time we have an alpha squared, we can replace it with a -1. So we would never have degree 2 or higher in the expansion like this. It turns out that this is a more general phenomenon. So we have to be very careful. There's a difference between parentheses and square brackets. So if I give you something parentheses, f parentheses alpha, that's the smallest subfield of L that contains the field f and alpha. F bracket alpha is the smallest subring of L that contains both alpha and f. Now, especially if you have a professor with messy handwriting using chalk, square brackets and parentheses can be mistaken very easily. Does it matter which I'm using? Wouldn't it be wonderful if parentheses were the same as brackets, if these two were the same object? And theorem 8.5 is yes. If you happen to be in the situation where alpha is algebraic over f, then these two are the same. What's the biggest difference between a ring and a field? No.
Wait,
We always like our things to be commutative. So you're right. I should say commutative ring. So we'll say commutative ring and field, because you are right. We don't assume that the rings are commutative. But there's a property that a ring does not have to have that a field does have. It has to have multiplicative inverses. So for a ring, we don't necessarily have to have inverses. For a field, we do. So as long as you're not 0, there must be an inverse. So for instance, f parentheses alpha contains the inverse of alpha, but there's no reason to expect that f bracket alpha has the inverse. Now we've talked a little bit about this, about when this might actually be the case. We did this calculation earlier. Let's assume that we have, f of alpha equals 0. So an alpha to the n plus an minus 1 alpha to the n minus 1 plus dot 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 plus a1 alpha plus a0 equals 0. And let's assume that this is the minimal polynomial. No smaller degree works. So what can you tell me about a0 if no smaller polynomial degree works? It's not 0, because if a0 was 0, then there's no constant term I can divide through by alpha, and since alpha is not 0, I can just remove it, and I would get a polynomial of smaller degree. It's important here that we are in a field, that there's no integral divisor, that there's no 0 divisors. Can somebody give me a ring where we have 0 divisors? Can you give me a ring where you have 0 divisors? Two numbers that clock, which clock? The clock in the room, the one behind us, right? Clock with 12 hours, 3 times 4 is 0. 6 times 3, is that 0? No. 6 times 4. Yes. So you can have a lot of different things multiplying to 0. You can have things that sometimes multiply to 0, but with other things don't multiply to 0. So we know a0 is not 0. So we can say that alpha times, an alpha to the n minus 1 plus dot 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 plus a1 equals negative a0, which is not 0. So alpha times negative an over a0 alpha to the n minus 1 plus dot 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 plus, I guess these should all be minuses. Doesn't really matter, but minus dot 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 minus a1 over a0 equals 1. And so here is alpha inverse. So we showed that we can invert alpha if alpha satisfies a polynomial of smallest degree, if alpha is the root of a polynomial of smallest degree. This is not the same as everything is invertible. I have to be able to find the inverse of 3 alpha squared minus 7 divided by 15 alpha cubed plus 11. I need to find the inverse of that. Well, it turns out we just have to find the inverses of polynomials. And so I'll leave it as an exercise that once we have alpha inverse, we can actually find the inverses to everything. What's really lurking in the background is if you have two algebraic numbers, their sum is algebraic, their product is algebraic. So if you have a number that satisfies a polynomial of finite degree, and you have another algebraic number that satisfies a polynomial of finite degree, then their sum satisfies a polynomial of finite degree, their product satisfies a polynomial of finite degree. So we can always get inverses to any element in the ring. The natural question then is, what polynomial works? If I know the polynomial of alpha and I know the polynomial for beta, what's the polynomial for alpha plus beta? What's the polynomial for alpha beta? And it could depend on alpha and beta in terrible ways. And so I will leave that as something for you to think about. All right, the next one, this problem should look familiar. So theorem 8.8. Let R be a commutative ring. Almost always our rings will be commutative. Little f of x will be a non-zero polynomial. Why do you think I want to assume f is a non-zero polynomial when I'm giving you a theorem about factoring f and finding roots? Yes, and that is the technical term. It's stupid to be asking this question if I give you the zero polynomial. What can you tell me about the factorization of the zero polynomial? What can you tell me about the roots of the zero? The zero polynomial is extremely well understood. What are the roots of the zero polynomial? Everything, right? So we exclude that case when I'm trying to build up the theory here because we know what's going on. So suppose alpha is the root of f of x. That means f of alpha is 0. then there is some polynomial g such that f factors. And in fact, not only is there such a polynomial degree g, but we also have the degree of g is the degree of f minus 1. And so this was a homework problem. And for A, what we did is we had f of x was an x to the n plus dot 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 plus a1x plus a0. We have f of alpha was an alpha to the n plus dot 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 plus a0, and this equals 0. So f of x is f of x minus f of alpha, and that's going to be an x to the n minus alpha to the n plus dot 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 plus a1 x minus alpha equals 0. I'm sorry, not equals 0. So f of x minus f of alpha is the following. Can you give me a polynomial factor of x to the n minus alpha to the n? X minus alpha. And you're just basically, look, if I take x equals alpha, then I get alpha to the n minus alpha to the n. So x minus alpha should be a root. And you should hopefully remember this identity from algebra. This is x minus alpha, x to the n minus 1 plus x to the n minus 2 alpha plus dot 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 plus x alpha to the n minus 2 plus alpha to the n minus 1. And when I multiply, you're going to get a telescoping. X times x to the n minus 1 is x to the n. X times x to the n minus 2 alpha is x to the n minus 1 alpha. And then the negative alpha, when it hits x to the n minus 1, will give us a negative x to the n minus 1 alpha, which cancels. And things just cancel marching down. So everything is going to have an x minus alpha. So this will just be equal to x minus alpha times crap of x and alpha. And this is going to be a polynomial of degree n minus 1. Because every term is going to have an x minus alpha. So that's my factorization for part A. Suppose R is an integral domain. Then if you have the distinct roots, we can just keep doing this and we can just pull them all out. And it can't be anything more. So continuing with the assumption that's an integral domain, part C, a non-zero polynomial of degree d has at most d distinct roots. Well, once you have d distinct roots, you would have this factorization. And what would the degree of g be? It would be 0. So g would have to be constant. So for part C, if it's constant, because it's an integral domain, if there was another root, if there was a d plus first root, then when I plug that in, I would get alpha d minus alpha 1. So alpha d plus 1 minus alpha 1. Then alpha d plus 1 minus alpha 2. All of those would not be 0. And since it's an integral domain, what's their product? Non-zero. And that's where we use the fact that it's an integral domain. If I give you, say, z mod 12z star, if I give you x squared minus 1, it has roots 1, 5, 7, and 11. This is the danger. We have to be very careful. We're used to, if I give you a polynomial of degree 2, it has 2 roots. If I give you a polynomial of degree 3, it has 3 roots. Here's a polynomial of degree 2, and it has 4 roots. So you've got to be very careful in taking your intuition and extending it. One of the few things that I've really remembered from my science classes in high school was there was a unit on special relativity in our AP physics textbook where it's talking about some of the results, and some of the results in special relativity, if you've never seen them before, are quite strange. And the sentence was something along the lines, while these results may seem surprising and counterintuitive at first, you have to remember that most people do not have experience traveling at 3/4 the speed of light. I love the most people. I'm trying to think, is there even one person who has experienced traveling at 3/4 the speed of light? If you're on a train, and again, all the special relativity examples, they always use train because that was the fast motion back then. If the train is traveling 100 miles an hour and you're jogging or running at 10 miles an hour on the train in the same direction as the train, if somebody on the ground sees you going by, how fast do they see you going? So the train's going 100 miles per hour. You're jogging in the same direction of the train at 10 miles an hour. How fast does it look like to someone on the ground? 10 miles?
Someone on the ground?
Yeah, so the train is going at 100. You're on the train, jogging on the train. So relative to somebody sitting down in the train, you look like you're going at 10.
Sitting down.
So somebody sitting on the train sees you going at 10 miles, but somebody at the train station, as you go by, how fast would they see you? 110. You know, the train's going 100, you're jogging on the train at 10 miles per hour on the train, right? So it looks like speed is additive. Speed is not additive. It's not 110. It's a little bit less than 110. But the amount that it's less by is so small that the experimental evidence looks like with an experimental error, the speed is additive. And so the mistake that physicists made is they said small velocity looks like speed is additive. We will extrapolate this to all speeds. No. As you get closer to the speed of light, the impact becomes greater and greater and greater. And so if you're traveling at 3/4 the speed of light and you're jogging at 3/4 the speed of light on something going 3/4 the speed, you do not look like you're going 1.5 times the speed of light. So it's very easy to make too much of a generalization from small results. So I just really want to warn you about this. Most of you are not going to be finding roots of polynomials, but you are going to be taking data from some small areas and trying to apply it in different settings. So just be aware, be alert that just because something holds in one setting does not mean it's going to continue to hold. Okay, so time for some definitions. So we're going to let F be a field. L over F is going to be an extension field. And then we will say F splits completely if we can factor it as some constant times x minus alpha 1, x minus alpha 2, all the way up to x minus alpha d. And so the alphas are in L, and the C is some invertible element. The alphas do not have to be distinct. And we'll say that L is the splitting field for little f over F if it splits completely in L, but there's nothing smaller that works. So for example, if I give you f of x equals x squared minus 2, that is equal to x minus root 2, x plus root 2. So this splits in where? So give me a field where this splits completely. Q root 2. Or Q root 2 cube root of 2. Or the reals. Or the complex. There's many fields where this polynomial splits completely. So the splitting field is the smallest field that works. And I'm not going to go through all the details. You can read the book. Basically, if I give you a polynomial, I can just add a new element to make this my root. And I can keep adding more and more elements until everything splits completely. And then the question becomes, is there a unique splitting field? And if I add roots in different ways, do I end up getting to the same field? Are these all isomorphic to each other? And that's a big result that you're not going to get something different depending on the order in which you add things. Now, in terms of just the impact of what you can see, let's get a sense of how things stabilize. If I give you a polynomial with integer coefficients, must it have integer roots? No. And that was a really fast no. So, 2x minus 3 equals 0. 3 halves is not an integer. All right, so what if I give you a polynomial with rational coefficients? Must it have rational roots? All right, you're very Anti today, so the answer is no. Okay, x squared minus 2 equals 0. The square root of 2 is not in Z. All right, what if I give you a polynomial with real coefficients? Must it have real roots? No. I mean, say what's the truth? All right, so yeah, so now you've got everybody being contrarian. It's not just you now, it's getting infectious. So we could give you x squared plus 1 equals 0, and we have I is not real. Oops, this should have been the rationals, not the integers. And I think you all see what is coming next. If I have polynomial with complex coefficients, must it have complex roots? So now I'm giving you a polynomial, f of x is, an terrible x. An x to the n plus dot 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 plus a0. Each ak is in C are all roots in C. What's the answer? Yes. So that's the amazing thing. Polynomials with rationals, you leave. I'm sorry, with integer coefficients, you leave. Well, what if I give you a polynomial with rational coefficients? Nope, not enough. Real coefficients, not enough. But once I have complex coefficients, once I add that square root of minus 1, doesn't matter what polynomial you give me, I don't have to add anything else. That's amazing. So we don't use the word fundamental lightly in mathematics. Other subjects might inflate and make every theorem feel good or every result feel good. For us, you've got to work to be given the title fundamental. Sometimes we use a different word. If you've done probability, we'll talk about the central limit theorem. That would be the fundamental theorem of probability. So you can go to various places and find lists of theorems that call themselves fundamental. You might argue a little bit as to, some of them putting on airs, but there's a couple of real basic ones that hopefully you've seen. Hopefully you've seen the fundamental theorem of arithmetic. Every positive integer has a prime factorization unique up to the order of factors. Or if you write the primes in increasing order, there's one and only one way to factor a number. We've seen that this is not necessarily true in other rings. We've seen cosine squared of x is 1 minus sine x times 1 plus sine of x. We've also seen things involving, the square root of -5. There can be some interesting things happening. Fundamental theorem of algebra, every non-constant polynomial over the field of complex numbers has at least one root. Well, that's not the same as it factors completely. Or is it the same? Is it enough to just have one complex root? Is that the same as it factors completely over the complex numbers? Yeah, it's the lather, rinse, repeat. As long as I have one root, I pull out that root, then I have a polynomial of degree 1 less. Oh, I still have complex coefficients. I factor. So once you have one root, you have them all. Now, what's interesting is if you try to do this over the reals, let's say I give you the polynomial f of x is x squared plus 1. No real root. So for instance, I could start off with a cubic. Any cubic is going to have a root that's real. And the reason is you go off to plus infinity in one direction and minus infinity in the other, because x cubed goes different ways depending on, are you going to plus infinity or minus infinity? So any cubic with real coefficients has a real root. And if you pull out that real root, you'll have a polynomial with real coefficients, but not every quadratic has a real root. The reals are not enough. The process breaks down. For complex, it's fine. There's a lot of versions of the fundamental theorem of calculus. I am not thrilled with the way they've stated it here. For every continuous function on an interval, the function g of x is an antiderivative of f on ab. To me, the only reason that this is worth studying is that this is the area under y equals f of t from t equals a to t equals x. The content of the fundamental theorem of calculus is the area under the curve from a to x is the antiderivative at x minus the antiderivative at a. And then the last is, you might have seen the fundamental theorem of linear algebra. Depending on who's teaching it, they may or may not have isolated this out. The row space of a matrix is orthogonal to the null space, and the dimensions add up to the number of columns of the matrix. Does that seem vaguely familiar? I'm just going for vaguely. Yes, okay, thank you. All right, so do they use the phrase fundamental theorem of linear algebra?
I've never seen that thing like within there before.
I don't think I saw that until I was in graduate school. And so, different people have different standards as to what they will call fundamental. It's one of the big theorems in linear algebra when you're trying to solve equations. If you're trying to solve ax equals b, b has to be in the column space. The solution is unique if the null space is just the zero vector, and there's all these connections between the dimensions of the different spaces. It's an important theorem. All right. The next one, let big F be a field, little f is a non-zero polynomial. There exists an extension field that's a splitting field. And the degree is bounded of the extension is bounded by the degree of f factorial. The factorial function grows. 5 factorial is 120, 6 factorial is 720, 9 factorial is a little over 300,000. It gets large somewhat quickly. I'm not going to go through this in detail. I'll let you see the book for part A. That basically, look, if I've got a polynomial, I can add a new element that will be my first root. And then I'll pull that out, and then I'll have a polynomial of smaller degree, and I add a root. And I keep doing this, the lather, rinse, repeat, until I'm done. Let's get a sense of just how bad this is, how long we might have to do this until we finish. So we start off with some polynomial f of x is x minus alpha 1 times g1 of x. And what can you tell me about the degree of g1? Let's say the degree of f is n. What can you tell me about the degree of g1 of x? N minus 1. Now, it might be the case that as soon as I introduce alpha 1, I'm done. For example, if I give you f of x is x squared minus 2, that's x minus root 2, x plus root 2. Once we adjoin the square root of 2, we're done. We don't need to do anything else. Once I put in that first root alpha 1, I don't need to worry about alpha 2. I get alpha 2 for free. Maybe my polynomial is a lot worse and I have to add a lot more stuff. If you go back to the polynomial that started everything today, if I add just that one root, do I need to add anything else to get all the other roots? I don't know. Right? Looking at this, is that going to be all that I need? Maybe, but it's not immediately clear. And so over here, it's possible that as soon as I add alpha 1, I'm done, but maybe I have to continue. Okay, well, if I have to continue, then I can write g1 of x as x minus alpha 2 times g2 of x. What's the degree of g2 of x going to be? N minus 2. And for alpha 1, the extension is going to be a degree n extension. So what I'm going to do is I'm going to start off with f, and then I'll have here f1. I'm going to put in alpha 1. I'll put in f of alpha 1, and so this is degree n. And I'm looking at the worst case, and then I might have to put in an alpha 2. And then worst case, that would be an n minus 1. And this is how you can see the worst case things could be would be a factorial. So does everybody see where the degree of f factorial is coming from? Is the worst possibility is if every single time nothing helps me and I have to keep adding something completely new. I want to just give you a sense of sometimes how calculations can be done. So here was a problem I got many years ago. Take the numbers 1, 2, ... 9, use each once and only once in the following. I'm going to take 3 fractions. And if I put in the numbers appropriately, it's going to add up to 1. So I was at a math institute, one summer many years ago, and somebody mentioned this riddle. And I'm surrounded by some of the top number theorists in the world, and they start trying to prove results about where the 5 or the 1 or the 9 must be. And I know as well, 9 factorial, that's around 300,000, 330,000. Would you like to do 330,000 cases? What do you think? Who's up for that? No. How about having your computer do 330,000 cases? I'm sorry? That's not bad. Now, this is where I was really intelligent and very proud of myself for this. Can somebody tell me, without loss of generality, where does the 9 live? Can you localize 9 at all? Yeah, one of the 3 things. So without loss of generality, 9 is in which fraction? The first. And what I realized is I am only running this code once. It would take me longer to code 9b in one of the first 3 places than to write the code inefficiently and go through all 330,000 possibilities than to actually take the time and write that 9 has to be one by breaking it up into 3 cases. 9 is the numerator, it's the tens digit in the denominator, it's the ones digit in the denominator. That would take more time to write than to just write the inefficient code and run it once. So I leave as a challenge to you to write the computer code and actually find what arrangement of the numbers work. Or of course, you're welcome to prove it theoretically and try to prove where the 9 and the 1 and the 5 must be. You're welcome to do that. How many solutions do you think my computer program returned? It is under 10. If you think about it, how many solutions will it return? I've got to put the numbers into these 3 fractions. I will agree with you, it's under 10. Once I tell you it's under 10, there should only be 1 number that works. 1 number under 10 that will work for the number of solutions. 6, why 6? Good, I have 3 fractions. There are 3 factorial ways to order the 3 fractions because addition is commutative. So my program should return 6 answers because I'm not putting any conditions about where the 9 must be. So this is a really good general principle. If you only need something once, it's often not worthwhile to be efficient. If I was writing this as a program that was going to be run on iPhones all the time, then any little bit of savings might really matter. And 9 factorial, that's small enough that the computer can work with this. But the degree of f factorial, that worries me because that grows rapidly. And so when I'm trying to get a sense of just how big is that splitting field, how far do I have to go before I'm guaranteed that everything splits? Well, sometimes I only need a theoretical result, but it's some field of finite degree. And this will definitely give me some field of finite degree. Okay, so now this is a great opportunity to look at something you've seen before with a completely different purpose. So big F is a field, little f is a polynomial. It's now allowed to be the 0 polynomial. And we write little f as a0 plus a1x plus a2x squared all the way up to adx to the d. And then the formal derivative is defined by just decreasing the powers of x by 1 and multiplying the coefficient in front of x by the power of x. So we have a1 plus 2a2x and so on and so on and so on. So we lose the constant term. Am I allowed to define a formal derivative like this? I'm allowed to do anything I want. I'm a professor at Williams. Oh, okay, I'm not allowed to do anything I want. There's certain things I cannot do. But this, I can do anything I want in terms of defining things mathematically. Could I define it to be 1a1 plus 2 squared a2 plus 3 cubed a3x, and so on and so on and so on. Sure. It's what's going to be useful. Could I define it as 1 over a0 plus x over a1 plus x squared over a2? Could I define the formal derivative as just take each term and take the coefficient and make it 1 over that coefficient? Could I do that? I am a professor, I teach at Williams. So I could define a formal operation, or I just replace ak with 1 over ak in front of the x to the k. What do you have to be careful about? AK is non-zero. So because some of the coefficients can be 0, I can't define the formal derivative to just be take the reciprocal of the coefficient. That would not necessarily be well defined. But as long as I'm not dividing by 0, I can do a lot of things. The question, of course, is when will this be useful? Just because I can do it doesn't mean that it's going to help me at all. So now we're going to prove a bunch of results. So you have the sum difference rule. If I give you f of x plus g of x, and I take its derivative, it's just f prime of x plus g prime of x. We are not using calculus. We are not taking a limit as h goes to 0. We are just formally defining the derivative and showing it has a bunch of properties. After the sum difference rule, what should I prove next? Product. I probably should have said maybe the constant rule first. If I have c times f of x, that's c f prime of x. Next would be product rule. If I give you f of x times g of x, and I ask for its derivative, that's f prime of x, g of x, plus f of x, g prime of x. What should I do next? After the product rule comes, can I do the quotient rule? Am I allowed to do the quotient rule? I have to worry about things being 0. Am I allowed to do the quotient rule? No. So if I try to do things that are not 0, I can maybe do the quotient, but I have to worry about the quotient rule. So I will do the chain rule and say if I have f of g of x, and I take the derivative, that's f prime of g of x, g prime of x. So for the proofs, do x to the n, let's say ax to the n plus bx to the m. It's the derivative of the sum will be a n x to the n minus 1 plus b m x to the m minus 1. And if I take the x to the n times x to the m and take the derivative of that, it's n plus m x to the n plus m minus 1. There's lots of ways to prove the results here. I could just prove things directly for the products and whatnot, but maybe what I can do is I can do things by grouping. I can just prove things work term by term by term and combine. So I'll leave this as an exercise for you as to how should I put things together to prove these results. Why do we care about this? Well, one of the things we're getting to is, it's been a while since we've had a definition, so let's take another one. So big F is a field, little f is a non-zero polynomial again. Why do you think I want the polynomial to be non-zero? Yes, zero polynomials are boring when you're trying to find the roots in factorization. Everything is the root of the zero polynomial, so we don't want to study that. So we have that there's an extension field in which f factors. And it's said, we say f is separable if the roots are distinct. And the terminology comes from the fact that, a separable polynomial, the roots are separated from one another. We don't have anything repeated. Conversely, if f has one or more repeated roots in a shaka, we call it inseparable. Give you the polynomial f of x is x to the 4th minus 2x squared minus 1. This is, of course, not a random polynomial. This lecture has been carefully prepared and crafted. This is x squared minus 1 squared. how can you factor x squared minus 1? Oh, sorry, I want a plus 1 here. Sorry, I want a plus 1 here. Sorry. So the factorization was correct. I just wrote down the wrong polynomial. Yes, thank you. X to the fourth minus 2x squared plus 1. It's x squared minus 1 squared. So how would you factor x squared minus 1? X minus 1, x plus 1, and then we square that. So it's just x minus 1 squared, x plus 1 squared. So this polynomial is clearly not separable. So one way to see if a polynomial is separable or not is to factor it. Well, factoring is hard. And so if that's the way we're going to tell, I'm in trouble. And again, this is the nice thing about using slides rather than writing things on the chalkboard is I can now go back to the start of the day and ask you, is this polynomial separable? If anybody wants to, right now, your entire grade for the class can come down to your answer. Are you really sure? It turns out there's a really simple way to tell if a polynomial is separable. So let's let big F be a field. Little f is a non-constant polynomial. Constant polynomials are pretty easy to understand. F is separable if and only if the greatest common divisor of f and f prime equals 1. Now we've got to be careful. What does the greatest common divisor mean? This is the polynomial greatest common divisor. So Mathematica is wonderful for calculations like this. It has a function called polynomial GCD. It returns the greatest common divisor of two polynomials. And so I gave it x squared minus 1 and x to the fourth minus 1. And the reason is because if you look at what we had on the previous page, I can also write this as, was I doing something slightly different? Yeah, that's fine. I guess I was looking at a slightly different polynomial. That's fine. So anyways, I was looking at something slightly different. So I have x to the fourth minus 1. I have x squared minus 1. And not surprisingly, x squared minus 1 goes into x to the fourth minus 1, x squared minus 1 times. Would you write it as -1 plus x squared? It's not a bad way to write it. You're writing constant term, then linear term, then quadratic term. So if this theorem is correct, then we've reduced determining whether or not a polynomial is separable, whether or not the roots are distinct, to just finding the greatest common divisor of two polynomials, f and f prime. Is it hard to find f prime given f? No, drop the constant term, decrease all the degrees by 1, multiply all the coefficients by the index. Not hard at all. The question is, how difficult is it to find the greatest common divisor? If I give you something that says, all you have to do is factor this number, well, we don't know a good way to factor numbers. Fortunately, it's much easier to find greatest common divisors than to do a full factoring. And the big thing that we're leading up to is theorem 826. If big F is a field and little f is an irreducible polynomial, if the derivative is not identically 0, then f is separable. So this becomes a really nice way to tell if you're separable. Just take the derivative and see if the derivative is identically 0. So I will explain about that. If f has characteristic 0, then f is separable. And so what does it mean to be 0? Well, remember, if I give you a field, the field has either characteristic 0 or it has a prime characteristic. So imagine we have the field fp. So this has characteristic p. Consider little f of x is x to the p minus 1. F prime of x would be p x to the p minus 1. And that would be identically 0. Because in a field of characteristic p, p is equal to 0. And so the polynomial has degree p, it's not the zero polynomial, but its derivative is the zero polynomial. It's things we have to be careful about. Think of the example from special relativity. Be very careful generalizing what you know from the rationals or the reals to these other settings, to these settings where we have the characteristic is not zero, where the characteristic is primed. So it all comes down to, is it difficult or hard to find the polynomial GCD? Well, if you remember, we talked about the Euclidean algorithm or the division algorithm, which allowed us to calculate the greatest common divisor of two numbers very quickly. And initially, when we were going through the Euclidean algorithm, it could be the case that every time we iterate, we only decrease the number by one. We start off with y is some multiple of x plus a remainder, and that remainder is less than x. And then we write x as a multiple of that remainder plus a new remainder, and that remainder is at most one less than the previous remainder. Every time we iterate, it's possible that the remainder only goes down by one. If that's the case, if x is of size 10 to the 200 or 10 to the 400, it's going to be disastrous in terms of how long it's going to take us. But it turns out for the Euclidean algorithm, every two iterations of the Euclidean algorithm, your remainder decreases by a factor of 2 from 2 times ago. So it's going to run in logarithmic time. So if you have something of size 10 to the 400, it's going to run in some multiple of 400 steps. It turns out that for polynomial GCD, every time you apply it, you reduce the degree of the remainder by at least 1. I do not want to write up the proof in full detail. So what I want to do instead is I want to just show you how it goes. So let's assume the degree of G is less than, say, the degree of F. And what I want to do is I'll write f of x as q1 of x, g of x, plus r1 of x, with the degree of r1 less than the degree of g. And we'll keep going down and down and down like this. And I'll leave to you, what would you do if the degree of g was the same as the degree of f? We'll start off with a lower degree. Why? Well, the case I'm looking at, I'm starting off with a lower degree. F prime is of lower degree than F. So let me just sketch how things go. Remember algebra 2? Remember you took something called algebra 2? Yes, and you had long division. You did long division in algebra 2 of polynomials. We're going to do that now. And now you'll see why I don't want to write things down in great detail. So here's f of x. So let's say f of x is, say, fn x to the n plus fn minus 1 x to the n minus 1 plus dot 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 plus f1 of x plus f0. And now I'm going to take my polynomial g of x. So I'll write that as g sub k x to the k plus dot 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 plus g1x plus g0. And I want to know how many times does the g polynomial go into the f polynomial? Well, I look at the leading terms. How often does the gk x to the k go into the fn x to the n? How many powers of x do I need? X to the n minus k. And what's the constant term I need? I want to get fn. I have gk. So what do I need to multiply x to the n minus k by so that when I hit it with the gk, I get fn? Fn over gk. Plus dot 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 dot. And since gk is not 0 and in a field, 1 over gk exists. So this is actually doable. And so when we do this, you can see that you will end up with a polynomial of degree smaller than g. And that will be our remainder. And then just lather, rinse, repeat, just keep doing, keep doing, keep doing, keep doing. Every time you do it, the degree of the remainder will go down by at least one. It might go down by more, you might be lucky, but worst case, it's going to go down by at least one. And so when we do that, we will end up getting, our result. We will be able to find the polynomial GCD, and the runtime is going to just be related to the degree of the large of the two polynomials. And again, I'm assuming here that the degree of G is strictly less than the degree of F. If they were the same, you can easily modify this. I was assuming that the degree was smaller because I'm applying this to F and F prime, and I know the degree is smaller. But I'll leave it to you to just handle the more general case. And then you just go through and you do all the algebra to show that this works, that you can find your Q1 and your R1. As you get further along in mathematics, you get to be a little bit more hand-wavy in what you're doing. You can't do this on an exam. You have to show me that you know what's going on. But no professional mathematician would write down all the steps for this. When you're learning, strongly recommend that you spend the time, write down all the steps, make sure you really understand what's going on. But the goal is to eventually get to the point where you can just look and say, yeah, I see the big picture. I see the general idea of why this is going to work, and not get bogged down in all the details. That I can see that, I'll be able to get all these terms, and when I finish, I will have something of small degree. You need to write it up rigorously, but once you've done that, you never write it down rigorously in any paper. All right, so let F be a field, and then let little f be a non-constant polynomial, then F is separable if and only if the greatest common divisor of F and F prime equals 1. And so I'm going to give a sketch of the proof. I don't want to prove the whole thing. I'll refer you to the book for all the details. So assume F is not separable. We must show the GCD is not 1. So if F is not separable, then I have to have some root that's repeated. So let's say alpha is repeated, so I have x minus alpha squared times something else, let's say g of x. What would f prime of x be if f of x is x minus alpha squared times g of x? So how would I calculate the derivative? Product rule. And it's the same calculation as from calculus. We just show that all this works. It's going to be 2x minus alpha g of x plus x minus alpha squared times g of x. So each one of them has at least an x minus alpha. So this is going to be x minus alpha times, let's call it, b of x, some function. And so now we know that the GCD of f of x and f prime of x is not 1, as it has x minus alpha as a factor. And then you can prove the other direction as well. But basically, if you're not separable, we can write the x minus alpha squared, and then you just go through, well, what if the GCD is greater than 1? Then you show that we've got something that's going to be a root of f. That will be repeated. Okay, so what I want to do now is just talk a little bit about what we're going to do in the next class. There's a limit to how much content I want to throw at once. We've got a lot of content that's come in today, and I always want to be mindful to make sure, because it is much easier to be at the blackboard speaking than to be in the seats listening. So if I give you some polynomial with integer coefficients, we define the content of f as the greatest common divisor of its coefficients. And what I want you to do is I want you to do some experiments. So write code and explore the content of f times g versus the content of f times the content of g. And so what you can do is take a bunch of polynomials. For each polynomial f and g, you can calculate the content, multiply them together, and look at the content of the product. Do you want to make a guess or conjecture about what's the relationship between the content of the product and the product of the contents? Ideally, they would be equal. And this should be reminding of the group homomorphisms and all this stuff. I can take the product of two elements in G and then apply my map, or I can first apply my map and send them to G prime and then apply the product rule in G prime. So the content of the product is the product of the contents. That would be a wonderful result to have, and it turns out that that is true. So we'll prove that in the next class. The content of a product is the product of the contents. And then once we have that, one of the applications is going to be Gauss's lemma. So if I give you some function f with integer coefficients, if it turns out to be irreducible over the rationals, then it's also irreducible over the integers. So a lot of what's coming up is to try to find when does a polynomial factor. After this, we will then look at irreducibility via the reduction mod p map. If I have a function, let's say with integer coefficients, I can reduce and look at it, in the field, fp. So this is characteristic p. So if p equals 7, then 7 is 0, 8 is the same as 1, 15 is the same as 1. If I have a polynomial that is irreducible mod p, it has to be irreducible in the integers. Because if it factored in the integers, then each of those would factor. Unfortunately, it doesn't go the other way. If you are reducible in this mod p reduction, that doesn't mean that you're reducible initially. And you will see a bunch of examples where, sadly, they do reduce, but the function is irreducible in integers. And then we'll end with Eisenstein's irreducibility criterion. So if I give you a prime p, and I give you an extremely special polynomial where p divides all the coefficients from the constant term up to the second highest degree, p squared does not divide the constant term, and p does not divide the highest degree term, then f is irreducible. And the first question you should ask is, wow, this is an extremely specific polynomial to be looking at. All the terms except the leading term are divisible by p. P doesn't divide the constant term. Will I ever have a polynomial like this? And the answer is yes. It turns out that there are some interesting and useful applications where your polynomials satisfy this condition, and this will allow you to deduce that it is irreducible. So again, in terms of content, we did a lot today. So we were talking about fields and roots, and we start off with, we give you some number. How do you figure out, what is the polynomial that this satisfies? You can prove that sums of algebraic, products of algebraic numbers are algebraic, but to explicitly write down the polynomial is non-trivial. I urge you to just try to plug this into Mathematica and see, is Mathematica smart enough to recognize that this solves that? I've deliberately not done that, so I'm eagerly awaiting what you find. We talked about, the differences between subrings and fields. If I add a new element, I initially have all combinations of powers of alpha. But if alpha is an algebraic number, then I only have finitely many powers I need to work with. And in that case, we get the beautiful result that parentheses are the same as square brackets, that the subring is the same as the subfield. We then talked about, splitting polynomial and trying to factor it, and your distinct roots and all that stuff. And we saw that just because your coefficients live in a given field doesn't mean that your roots live in that given field. But once we got to the complex numbers, we didn't need to add anything more. Just adding the square root of -1 was enough to get everything. We talked about how this gives us the fundamental theorem of algebra, and a little bit about some of the other fundamental theorems, but basically every polynomial with complex coefficients factors completely over the complex numbers. We then went and we talked a little bit about what is the splitting field. That's the smallest field, which everything factors, and how far do you have to search for the splitting field? How big of an extension do you need? It could be quite bad with the degree of f factorial, but maybe it's not so bad. Maybe it's much smaller. And then, of course, a question which we are not studying now, but is a really important question is, if I try to add the roots in a different order, will I create a different splitting field? Or do I always get the same splitting field? It would be potentially scary if it matters which order you do operations. We talked a little bit about what does it mean to be a formal derivative. There's no calculus, there's no limits going in here. Just, formal definition, but all the rules from calculus hold. And this allows us to have a really nice condition to find out when can f be written as a product of distinct roots. And we got to this really nice condition that it's separable if and only if the greatest common divisor of f and f prime is 1. And this is actually nothing to be afraid of because it's actually not that bad to find if the greatest common divisor of f and f prime is 1. So for example, if I want to factor two numbers, that's difficult. If I want to see if two numbers have a common factor, that's easy. So you have to be very careful as to what are you trying to do. I'm not trying to factor f and f prime. That's one way to solve the problem. I can compute the GCD by factoring f prime, and then just taking whatever appears in both. And that's my GCD. If that's how I found the GCD, then this is a useless, for any practical computation. But what we can do is we can actually compute the GCD without fully factoring f and f prime. That's amazing. And then we ended by talking a little bit about the content. And you should have enough coding skills that you can write a little computer code to do this. You want to get to the point where you can use the computer as a tool to explore, to gather data, to make conjectures. And this is the 21st century. You have to ask, what tools do you have that they did not have 10 years ago, 100 years ago? We are talking as a community, what do we do about things like ChatGPT? Somebody from Mathematica was here recently. There was sadly issues, so he couldn't show me everything, but I got to see a little bit where you can now, there's an AI interface for Mathematica, where you can say, write me a code to simulate 1,000 coin flips from the following distribution, plot the distribution, find the best fit normal. It's amazing what you can have these programs do, and it's only going to get better. I have a Boston accent. When the voice recognition software came out over 2 decades ago, it's like, enter your reservation code, 35 it was just, and now they have AIs that handle all the customer service and can, for many people, just navigate you completely through. So you guys are young. You really want to think about which way are the fields going. What tools do you want to get? You want to learn how to use AI. You want to learn how to use computer programs. Old people, it's harder for us to learn stuff. You guys are younger. The time you spend now will be extremely worth it. So strongly urging you to do stuff like that. And then we ended with a brief comment about how stuff like this is going to lead to things, such as the content of the product is the product of the contents. It will lead to Gauss's lemma. And from this, we will get some conditions as to when things are irreducible. All right, so this is a good place to stop.